Conductors and electrostatic equilibrium. In this presentation, we will explore the outline of key topics regarding conductors. We will begin by discussing the fundamental properties of conductors in electrostatic equilibrium. Following that, we will examine the behavior of the electric field both inside and outside these conductors. We will then look at how charge distribution is affected by surface curvature. Next, we will establish the concept of the electric potential of conductors. And finally, we will cover the interesting applications of cavities and Faraday cages. Let us define what we mean by conductors in electrostatic equilibrium. A good electrical conductor contains charges, specifically electrons, that are free to move around. When there is no net motion of these charges, we say the conductor is in electrostatic equilibrium. In this state, a conductor exhibits four key properties. First, the electric field is zero everywhere inside the conductor. Second, any net charge resides exclusively on the surface of the material. Third, the external electric field is perpendicular to the surface, and its magnitude is equal to the surface charge density, sigma, divided by the permittivity of free space, epsilon 0. Fourth, the surface charge density is highest, where the radius of curvature is smallest. Let us delve into the first property, which states that the interior electric field must be zero. Why is this the case? If the electric field were not zero, the free electrons inside the conductor would experience an electric force. This force, equal to the charge Q times the electric field E, would cause the electrons to accelerate. However, this continuous motion directly contradicts our definition of electrostatic equilibrium, which requires no net motion of charge. When an external field is applied, the charges rearrange themselves rapidly to cancel the internal field. This state of equilibrium is reached almost instantaneously, typically on the order of 10 to the power of -16 seconds. The second property states that any net charge on an isolated conductor resides entirely on its surface. We can prove this using Gauss's law. Imagine drawing a Gaussian surface just inside the outer boundary of the conductor. Because the conductor is in equilibrium, we know the electric field is exactly zero everywhere inside. Therefore, the net electric flux passing through our imaginary surface must also be zero. According to Gauss's law, if the net flux is zero, the total net charge enclosed by the surface must be zero as well. This tells us that no excess charge can exist within the bulk of the material, so all excess charge must be distributed on the exterior surface. Moving to the third property, we look at the electric field just outside the conductor. This field must be strictly perpendicular to the surface. If there were a parallel component to the field, it would exert a force on the surface charges, causing them to move along the surface and breaking the equilibrium. To find the magnitude of this field, we can use a small cylindrical Gaussian surface that pierces the conductor's boundary. The flux through the inner flat face is zero because the internal field is zero. The flux through the curved side is zero because the field is perpendicular to the surface. Thus, the total electric flux is simply the electric field E times the area, A. By Gauss's law, this equals the enclosed charge over epsilon 0, or sigma times A over epsilon 0. Canceling the area gives a resulting magnitude where the electric field equals the surface charge density sigma divided by epsilon 0. Now let us discuss the electric potential of a charged conductor. A key consequence of the first three properties is that the entire surface of any charged conductor in equilibrium is an equipotential surface. If we consider any 2 points, A and B, on the surface, the potential difference between them is the negative integral of the electric field dot the displacement vector dS. Because the electric field is always perpendicular to the surface displacement, dEs, this integral evaluates exactly to zero. Furthermore, because the electric field is zero everywhere inside the conductor, no work is done moving a charge around inside. Therefore, the electric potential remains constant throughout the entire interior and equals the potential at the surface. This slide visualizes the relationship between potential and electric field as a function of the radius for a solid conducting sphere. For a sphere of radius r carrying a total charge q, the behavior differs inside and outside. Outside the sphere, where the radius r is greater than r, it behaves like a point charge. The electric potential, V, equals Coulomb's constant Ke times Q divided by R, and the electric field, E equals Ke times Q divided by R squared. Inside the sphere, where R is less than or equal to R, the electric field E drops abruptly to zero. However, the potential, V, remains constant at the surface value, which is Ke times Q divided by R. Note carefully that while the electric field is zero inside, the electric potential is constant but not necessarily zero. Our fourth property addresses the surface curvature effect. Consider two conducting spheres of different radii connected by a long conducting wire. Because they are connected, they form a single conductor and must be at the exact same electric potential, V. The potential is Ke times the charge Q1 over radius R1, which equals Ke times charge Q2 over radius R2. If we compare the ratio of their electric fields, E1 over E2, we find it equals the inverse ratio of their radii, R2 over R1. This mathematically demonstrates that the electric field is strongest at the surface of the smaller sphere. In general, for any irregularly shaped conductor, the electric field is strongest where the radius of curvature is smallest, such as at sharp points. Consequently, the surface charge density sigma is also highest at these sharp points. Let us explore cavities and Faraday cages. If a conductor contains an empty internal cavity with no charges inside, that cavity is a completely field-free region. Because the entire conductor forms an equipotential volume, all points on the walls of the cavity share the same exact electric potential. This uniform potential forces the electric field to be zero everywhere inside the empty cavity. This physical principle is the basis of a Faraday cage, which is a conducting shell or mesh designed to shield its interior from any external electric fields. Common real-world examples include elevator cars, which often cause mobile signal loss by blocking electromagnetic fields, and automobile bodies that protect passengers from external electrical discharges like lightning strikes. Let us apply these principles to an example involving concentric spheres. We have a solid insulating sphere with a positive charge Q, surrounded by a concentric conducting spherical shell carrying a net charge of -2, Q. We analyze the electric field in 4 regions. In region 1, inside the insulating sphere, the field increases linearly, with E1 equal to Ke times Q times R divided by the sphere's radius a cubed. In region 2, the gap between the objects, the field behaves like a point charge, so E2 equals Ke times Q divided by R squared. In region 3, inside the material of the conducting shell itself, the conductor is in equilibrium, so E3 must be exactly 0. Finally, in region 4, outside the entire setup, the total enclosed charge is Q minus 2Q, leaving a net charge of -Q. Therefore, E4 equals -Ke times Q divided by R squared. To summarize the key properties of conductors in equilibrium. First, the electric field E is strictly 0 inside the conductor material. Second, any excess net charge will reside solely on the outer surface. Third, the external electric field is perpendicular to the surface, and its magnitude equals the surface charge density sigma divided by epsilon 0. Fourth, The charge density sigma is exceptionally high at sharp points where the radius of curvature is small. Additionally, the entire volume and surface of the conductor remain at a constant electric potential. Finally, any hollow conducting shell will act as a Faraday cage, shielding its interior from external fields. We conclude with a couple of review questions to test your understanding. First, consider why the electric field must be strictly perpendicular to the surface of a conductor in electrostatic equilibrium. What would happen to the surface charges if it were not? Second, if a neutral conductor is suddenly placed in an external electric field, how is it physically possible for the net electric field inside the conductor to become exactly zero? Think about how the free charges move and redistribute themselves to create an opposing internal field.